everybody. Anyway, this is Don Lemke, WB9MJN. He's our featured speaker today for our Friday 4 p.m. seminar, speaking on Infrastructureless, my mistake on the program, Packet Radio Network.
Yep.
Don has been working on some very interesting antenna stuff and has some pretty cool information to present to you today. So I will turn it over to Don.
Okay, thank you, Greg.
Get their handout from the back? Okay.
I'm Don Lemke. I've been involved in packet radio here in the Chicagoland area since about 1986. Helped K9NG set up some of the original 9600 baud links using his modem, and which then grew into the G3RUH modem, and there's a variety of them now. The 0.5 GFSK modem. Infrastructureless packet radio networks. What do I mean by infrastructure? Infrastructure is kind of any third-party station that relays your transmission. We all got started on 145.01. We quickly found out that we couldn't all coexist on 145.01, at least here. And so we started to build these third-party sites. Some of them were in people's houses, and but most of the best ones that lasted the longest and worked the best were in commercial sites and just like regular repeaters. And so that's what I mean by infrastructure, is those sites. What I'm talking about today is how can we move forward in packet radio without having third-party sites. They have the only infrastructure required to be the infrastructure of all the sites of all the users who participate in the network, with no sites really dedicated to provide better linking and so forth. So let's go from there. So the infrastructure is going to be provided by the accessing and using stations only. That's what I mean by infrastructureless. And we've gone through infrastructure now, and we've had some pretty good luck with getting infrastructure here in the Chicagoland area. And but it's getting tougher and tougher and tougher. You know, there's a lot of problems with infrastructure. It's very time intensive. The first problem is location, location, location. The best infrastructure sites are third party. Nobody within the group is at that site. So when they're using the resource, they're not interfering with its capacity. Good third-party sites in this day and age of cellular telephone, GSM, PCS, etc., implies commercial demand, pagers especially too. We're getting harder and harder with the existing base of third-party commercial sites that we occupy as hams on voice repeaters to find good third-party sites for packet and digital modes. Another problem with a third-party infrastructure site, commercial site, is it takes too much time to install and maintain. We spend a lot of time doing that rather than moving forward in technology. And so it's an ongoing problem to keep it maintained, and even when you get it installed, there's been times in the Chicagoland area where, because we didn't get things installed in time, we kind of lost the opportunity. So it gets difficult. And another problem with third-party sites is, since there are so few of them and various groups within packet radio itself, a lot of cooperation is needed to make all this work together. It becomes top-heavy politically, and politicians like to compete to show that they deserve to be the politician, and other people deserve to be the workers, or whatever. This may be a negative view of things, but I mean, there's been many times where we've had competing groups self-defeat, and we lose an opportunity that would have been great. One example of that was we had a packet regenerator in Hinsdale, and we had one group kind of cause a big problem about that, and so we lost the use of $10,000 worth of equipment. We didn't pay $10,000 for it, but that's how much we would have paid for it if we would have bought it all new, and didn't have a lot of it donated. And so it sits there doing nothing now. It's basically because of politics. But so we have all these problems. These are some of the problems with infrastructure. The other bigger problem with infrastructure is the economics of an infrastructure-based network. That's typically a network where there's a central site and you have dedicated radio equipment at it, and then you have cheap high production access radios. You know, this is typically your D410 by Cantronics, 9600 baud access radio, the tech radios. They're cheap because they're high production. And they're cheap because they don't have to do a lot technically to get into a hub, into some kind of infrastructure. And that is the way that radio has been done since the beginning. This is how broadcast radio works. You have an AM receiver that's very small and cheap with a big monster tower to transmit to it. And this is the way things have been in radio, and this is probably why we started this way within our packet radio networks as well. The problem here with packets, though, is that unlike broadcasting, is that the linking radios being low production is a problem. As an amateur radio type like situation, there's for the linking radios, there's no real standards to build the communication to. There are a few K9NG, the WA4DSY, but you need a lot of these linking radios, and they're not necessarily at any one site, but you don't have a lot of sites, you don't have enough linking radios to make enough production to make them inexpensive. And so thus they're expensive. And you can talk about semantics. Some people like to spend time and not call it money, but it really is. And some people like to spend money and save time. So either way you think about it, because they're low production, these linking radios, they're expensive. This leads us to the catch 22 145.01. And the catch 22 145.01 is that cheap access radios are almost useless for networking if you don't have any low production infrastructure. Low production infrastructure is too expensive, so the access radios really are not cheap. They're cheap to buy, but in order to use them, they're expensive. This is kind of the catch-22 we've been in for a while now. I'm open to any kind of interruptions and comments and discussions along the way here. I've kind of laid this thing out, and this is kind of controversial, at least it has been when I've talked to people on the air about it. Does anybody have any kind of comments or debate about it? Go ahead.
Well, our experience in southeastern Minnesota is this is right on.
Okay. 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 Yeah, the Bay Area is politically limited, and Minnesota is more population limited. You got the opposites. You got the opposite population densities, and you got the same problem for different reasons. So it's kind of an ongoing thing. We have a network. We have a little gateway to Simi Valley, and the networking, trying to go through a NetROM network into the Bay Area in LA. Is that the right Bay Area?
North of that, San Francisco.
Oh, okay. Yeah. But it gets very difficult because there's not a lot of cooperation between various network node operators, and NetROM is very node operator intensive. So if it works right, and you can see all these network links and things out there, but it just doesn't work like it does when you have a nice organized networking problem. Another problem with infrastructure is siting. Let's say you get lucky and get a good site. Now you have your link infrastructure all at that one site. What happens if they can't get to another site? You're kind of fragile in this. Your network is fragile in this way. The problems we've seen here in our area has been noise level variation and multipath. Noise level variation is probably partly due to the 0.5 GFSK modem. A lot of people, but it is a real problem. in regards to this as well. A 0.5 GFSK modem is not FM voice, and consequently it's much more sensitive to noise than FM voice. And people plan their networks based on their FM voice experience, and then they kind of get stuck when they have an impulse noise source that's stronger than the signal they're trying to receive, and that causes a high bit error rate with the 0.5 GFSK modem. Even though you can talk right through it because it's a very short duration pulse on voice, no problem. We've had this experience with a site in Gurnee, Illinois. It worked very well for many years, but then there was a lightning hit on a transmission line just about 500 yards from this site, and it hasn't been able to copy a 0.5 GFSK from our downtown site since. So we've pretty much been decommissioned by us. Multipath, and you can even see this at 9600 Broad. When you have a narrowband signal, the fading looks flat, but it's really not. But in effect, it's flat. If you have, in our wormhole I was talking about, this is maybe not exactly the same thing, but that's an indoor 1.2 gigahertz link, a little horn antenna that shoots through a building to get 500 yards across the highway to another. And depending on where they park the coffee cart, it either works or not, because we're getting multipath from the coffee cart within the building. But on a larger scale, you get this same problem. We tried to set up a site in Hinsdale, Illinois, from Naperville, Illinois. And if you look at a map, Hinsdale, Naperville, and downtown Chicago are all in a line. And the link is on 220 megahertz. If you're not familiar with the history of 220 megahertz, it's our first band that's shared with radio location in the United States. And the reason it was shared with radio location, it was the first band that was used for radar anywhere. It wasn't used for aircraft radar, it was used for naval radar. And two Navy lieutenants were setting up an early spark transmitter or something, and they wanted to talk across the harbor mouth. And they noticed the signal faded when a ship went through. There was multipath off the ship, and they noticed that. And so in the history of naval conflict, there's been many cases where navies have snuck up into harbors, blockaded the front of the harbors, and blown up battleships in the harbor that can't maneuver because they're all in harbor. And so the United States Navy wanted a protection mode for this type of situation, so they came up, they found a band which reflected battleships primarily very well. And that band is 220 megahertz, and for radar purposes. And so now take a battleship and stand it straight up, and what do you have? You have a skyscraper. Downtown Chicago is full of skyscrapers. So what we were seeing with our site in Hinsdale, Illinois, is that with the proper location, the proper conditions, the reflections off the skyscrapers in downtown Chicago were corrupting our packets, even at 9600 baud. And the path between these downtown Chicago and Hinsdale is about 15 miles, and from Naperville to Hinsdale is about 15 miles as well. And so you have to consider multipath, and when your environment's varying, the multipath varies too. And so you can have a path that works perfectly at night, and during the daytime there's people and airplanes flying around and you have problems with it. Multipath, the time domain side of multipath is delay spread. We'll get into a more exact location of that, but it's more impacts wideband signals or long-range paths. And when we were in between, on our 9600 baud experience, we were in the Hinsdale site with an oscilloscope, and sometimes we wouldn't have a signal, but other times there was plenty of signal, but it was really screwed up. And we'd go over to the Naperville site, look at the transmitter's perfect. We'd go back to the Hinsdale site. Why is the signal so screwed up? That's an example of delay spread. The multipath, it was such, and you can see this on TV when you're trying to receive it in an apartment building. You see delay spread problems. You got plenty of signal strength, but your color burst oscillator may be interfered with, and your colors go crazy. You see different images staggered throughout the picture. This is all a delay spread problem. The reflections are coming in at a different time from the main signal. And so we'll talk more about that later. But if you're at one site with one one link or two links, if that link gets knocked out by delay spread for a period of days because of whatever is happening, you've lost your utility and all your eggs. That's the problem with having infrastructure third-party sites is all your eggs are in one basket. Another thing here is, let's see if he's got this. There it is. Okay. Hub access systems hub access is system-wise inefficient. Now, I'm probably not talking to the choir in this regard with regards to cellular telephone. Cellular telephone has been a highly efficient, highly economical system, but the basic idea, although it was a paradigm shift in efficiency above two-way radio, in this day and age, we can start to see that it is not that efficient either, and here's why. When you have various hubs, they're fixed in location, and they're all the users are within this area, or within for each particular user, for each site here. So now, this transmitter, when it wants to talk to any of the users within the area here, pretty much has to come up to full power to cover the whole area. And so even though it may only need to cover this area to talk to an accessing station, it is using this complete area, even though it only needs this area. And if you have multiple sites around here, multiple users, when this guy needs to talk to the hub, he only needs to be accessed, and so forth. So you have a great inefficiency in your area with the hub access system because you really don't need to use this whole area, but because you're talking to this station and you may later have to talk to this station, you end up having to use this whole area. Another station over here, for example. And you can't move these hubs around and lower their powers and increase their powers dynamically, and this all leads to the inefficiency. And so another problem with Omni antennas, of course, is there's no protection from multipath noise or interference, as we talked before. If you're putting up an omnidirectional hub, which is what we do in ham radio because it's cheap, you don't have any protection from that. Okay. And you have an inefficient use of bandwidth, area, time, resource, because that's what we have. You have a triangle to get out to a particular user, and instead you're covering a whole circle. Even if you go to a sectored hub, you still have the inefficiency. And because if you're trying to talk to all the stations within this sector, when you're talking to the ones close, you're still using this whole area of the sector to talk to this guy, when you really only need this much area, this small little amount. Okay. So now another thing we might want to consider is what happens when we go to megabaud rates. This becomes a problem with and we'll get into why we want to do that. But megabaud rates are a good fraction of are small with respect to the free space propagation time. In free space, each packet the energy travels at 3.34 microseconds per kilometer, and so that's 3 bits at 1 megabaud. Which isn't too terrible if you're only going a kilometer. And if you're going to go at 10 megabauds at 32 bits, it's getting even worse. But if you want to do a megabaud and a regenerator, your round-trip path could be 40 kilometers, and at 10 megabits per second, that's 120 some bits. So you're starting to get a large uncertainty time between the start of the packet and the time it's going to arrive, and when you have a random network. So this becomes inefficient of how do you access, if you're trying to do carrier sense multiple access, channel access, how do you access the channel without colliding? Right now we have that problem just because we can't hear each other. But when we start to go into the future and we start to do megabit data rates, we're going to have that problem because we may be able to hear each other, but we don't really, but I mean, we heard each other, we're hearing the start of the packet when the packet's already over or partially through, so it becomes an access problem. In small cells, to get over the hidden station problem, there's various protocols out there, and they use kind of a request to send and clear to send type handshake to access the channel. And if you try to do this at a megabaud, the waiting time to make sure that to make sure that the channel is clear, like with MACA, it sends out a request, and if it doesn't hear, I'm not exactly sure, but some of these, I'm a bit weak on this one. But when it needs to access the channel and wait for a response to see if the channel is busy, there's an uncertainty at megabaud rates that it's going to have to wait even longer. So that introduces an inefficiency. It's been a few years since I talked about this. I did have an email back and forth with Karn on this on one of the news groups about where he said that they would have to add some kind of locator code into the MACA so that they could be sure that the returning packet that they had waited long enough before they sent their packets. But this is an advantage for hub systems if they use synchronous access. That's the type of access where the hub is a master. Do you have a question?
Talking about before, about how long you have to wait. In the MACA protocol, the request to send message contains the length of time it expects to be occupying the channel.
Yes.
And the clear to send message repeats that for the benefit of other people so they know how long to back off. Is that the question?
Yeah, but how long that time has to be with a group of stations that are randomly distributed in MACA is going to be variable depending on the distances involved, and since these distances are all random depending on geometry, you probably have to add, in addition to that time, a location so that you can then know how fast he can respond. And Phil would probably be a better person to go.
You're looking at the propagation time?
Yes.
I would expect the propagation time to still be rather short on the air time.
Well, I am talking at 1 to 10 megabaud. So, I mean, if you got a 40-kilometer range, that might be that's 133 bits. But if the guy's right next to you, so with MACA at 1200 baud, it doesn't really. So you don't have that problem. But as you go far. Right. We're talking 1,500 feet or 1,500 meters or something like that. So the ham radio network has longer ranges in it than local area networks, and so that's the little bit of difference there. So we have to consider this when we think about the next steps. So, but I mean, with a hub system, you're locked into ranges because you are trying to maximize economy by having the linking station at one site. And as you have a big hub with a bigger the range and more economical, the more the uncertainty becomes, and it becomes a problem in how do you develop an access technique. But you can do this synchronously, where the hub is a master station that puts out a timing type situation, a time pulse, and then each site is ranged, and then the permitted times of starting to transmit are all calculated out, and so and they do this in cable systems. All the little cable data boxes start their transmission back to the master station at a particular time, so that the master in time sees each frame come in perfectly aligned, one right after the other, no wasted time in between. So we don't do synchronous access here. I think maybe in Germany they do, DDMA or something like that. Okay. So things have changed since we started in 1986 or whenever you guys started, or before or after. When I first started in packet radio, we wanted to take advantage of the digital mode of communication's main advantage over analog, and that's repeating. You can repeat over and over again without any corruption of the signal. And that meant long distance. And I was a kind of a repeater DXer back then, and I wanted the repeater DX 3 repeaters, not just one. So, but that's kind of gone by the wayside, and I think what's replacing it is higher data rate. And the higher the data rate, the farther you can go, whether you're going by wire or radio. And the next thing is, we originally were trying to get full RF coverage throughout the whole United States. That was a goal, and it hasn't happened. It doesn't look like it's going to happen. And what's replacing it really is the high data rate path to the internet. What we really want is to be able to talk to what a lot of people want right in this day and age is higher data rates, so that they can keep up with the rest of the world who's doing TCP/IP as a regular course of things. We no longer have to do full coverage because we can always use the internet to fill in to get to where we want to go. So before we didn't have the internet to go to, so we wanted full coverage. We were going to get full coverage, but by going to the internet now, and not necessarily all on RF. It makes more sense that we use RF as the last mile solution. Applications bonanza, and if we do this, we can, of course, we do web surfing on 9600 baud through one of those antennas from our apartment. Works pretty good. We would want to do voice over the internet, for example, for repeater linking. And it would be nice if the repeaters in an area could shoot the last mile back to a common gateway. Packet TV, CUCME, is a program package that's out there where you can get on the internet and talk to watch and have packet TV conversations and QSOs, only it's all wirelines. It would be great if we could do that on TV, on RF, just through our computers. Remote shared computing applications like Java, etc. And whatever new happens, we want to be able to have a system that if somebody posts a new application that will run under Windows 95 or Mac system on the internet, we can just plug it into our system and use it. We don't have to re-engineer our RF system or our networking system for every new application that comes down the line, which is where we are right now. So we want to do metropolitan area networks. This becomes the hot topic versus overland linking as it was before. So we want to make an internet to the internet is now the overland network. We don't need to do the overland network anymore. We need the metropolitan area network, and we need it to be really good. The metro area radio can be faster than the phone line modems, and phone line modems right now are about topped out, 33.6, 56 kbaud. That's going to be it for them for a while until they come up with ADSL, which a lot of the telephone companies are against because it means a lot of work in their infrastructure. And we wanted, with the metropolitan area network, it should have high speed into the internet. Now, a lot of people have been playing around with this, and they've learned a lot, and they do a lot. Typically, two guys want to link together, or there's a guy in a college and he wants to get into his college resources when he's at home, and they set up. They use wireless local area network things as outdoor bridges, which they really aren't intended. Although a lot of different companies say they'll work like this, and they do work like this, but they will work like this if you're the only guy in the area using them like this. Because we haven't designed a system, a networking system on RF for them. They are nice little, what they are, for indoor, sheltered and shielded from the real mean interference laden RF network, RF world out there. So they are what they are, but as far as a networking solution, they're a dead end because they'll work for a limited number of users in the immediate area, and then they become interference laden. The 11 dB processing gain that's used in these things typically is intended to avoid interference with little wireless mics like I'm wearing right now and stuff like that. I'm not belittling these things. They're great. They're a good start, but they're not a network station. They are a local area network, and they're not a metropolitan area networking station. Can we overcome the ham radio economics of infrastructure metropolitan area networks? I think we can, and I think we need to think about a new kind of station, a network station. It's a station that is designed from the top to the bottom to do networking, it's not a patch together of a TNC or a radio and various combinations thereof to make a network. It's a radio concept to do networking, digital networking. We want some, and we need to get, in order to do this, it needs to be high production. The higher something is in production, the more sophisticated technically it can be. And that's the key to doing something far enough in advance that will suit our needs for a long future. One type, we want a unit. These are the engineering goals that are economically related for such a unit. We want a unit that's one type fits all. If you have a packet radio digital person, he can use this unit. If you have a repeater voice link guy, he can use this unit. If you have somebody who's doing TV with his neighbors, they can use this unit. We want to go back to the original goal in packet radio, that we had a network that served everybody. So the advantage of this is that you can sell it. If the packet networking kind of goes down in your area, but these two guys, your neighbors, want to do TV, you can sell it to them. It's a liquid asset. And the more liquid it is, the more people will want it because they can use it and use it. Something along the paradigm of an HF radio. You can buy an HF radio off the shelf these days, and anywhere in the world, hook it up to an antenna and use it. And then you can go anywhere else in the world and sell it. And that makes it a very powerful production. There's a lot of HF radios being built. There's a lot of high technology going into HF radios because there's enough production to make them. And we want it to have a metropolitan area coverage capability, although not necessarily directly, but in concert with units of like situation. And preferably neighbor-to-neighbor throughput should be much greater so that you can do TV with your neighbors at a megabaud. What we have here are a bunch of, those were the economic solutions that impact the technical design. And what do we have to, what resources are out there that we can use to make this happen? Well, we have bandwidth. If we use wider bandwidth, we have to use less time. We have to use it in less time. We have to be quicker with it, or else we're not as efficient. We have geographical area. Right now, like I explained with the hubbed antennas and omni antennas, it's not very efficient because we're using a lot of it, a lot of area for a lot of time when we really only need a little small sliver of area. And so one way to take care of that is directive antennas. And we do this on VHF weak signal work all the time, but more for range rather. But if you were in a space shuttle flying over a weak signal contest, you would realize the great impact, the great multiplicative factor in bandwidth utilization that you get from this as well. And we have time. We have this time and to use the spectrum, and we should use it when we can, and we better use it when we can, or else we won't get done what we want to before the weak signal contest comes along, or somebody else wants to use it for something else. I mean, we're all sharing this within ham radio, and we can either go fast or slow, but if we go fast, we should use less or slow, we need to use less bandwidth. These are our resources. And to help people remember this, it's always nice to have a unit. I'm calling this unit the megabaud kilometer for how many megabauds over what distance, divided by the bandwidth in megahertz, the area used, kilometers squared, and seconds, the time in seconds. And I propose we call this the one Costas, because Mr. Costas of the Costas Loop fame also did a paper on the interference limited networks, radio networks, and he used ham radio as the ultimate example thereof. So to help, I think I got the name right?
Which is that the Shannon radio?
Maybe it should be the Shannon.
No, I mean, the title of this, what's the title of it?
I've just heard this on email, but
that's the Poisson Shannon of the radio.
so, but this is a very important concept, and it's worthy of a unit so that we remember it, whether we actually use it in calculations or not. We probably will in the future, but maybe not in the immediate future. It's a unit of network utilization of the resource. Megahertz is bandwidth. There's kilometers in there twice. It's written like that so that it realizes we're talking range on the top, an area used to accomplish that range on the bottom. Megabits, yes. Or megabaud. Yes. Well, no, yeah, symbols or megabits per second. You're saying megabits. It could be megabits per second or megabaud.
There's a second in the denominator as well. That'll be a second from
That's the squared, for kilometers squared.
after the km squared, you have time second.
Yes, how much time of the resource you use.
So it's a bit rate.
Yeah, it is a bit rate in the numerator. So we got so it should be megabit, kilometer, megahertz, kilometer squared, second squared. Or it could be megabit, not megabit per second, megabit, kilometer, megahertz, kilometer squared, second squared. So this is data, and by having two, I don't have it on here, but it should be second squared. That would be data rate. The 1s is how often. No. Maybe you're right. Maybe I wrote it right the first time. I really don't need a rate. What we need is overhead. This is a unit of data that you get across in that time.
So 1 hertz cancels 1 second. And 1 of the kilometers in the numerator will cancel a kilometer.
Yeah, I wrote this as a conceptual thing, not as a mathematical one.
Well, you're proposing a unit of 1 Costas, and I was wondering whether some of the...
So this is going to be megabit, not megabit per second. Megabit. So it's how much data. Kilometer, how far did you get that data?
Yeah.
Divided by megahertz, how much bandwidth did you use to get that data across? Divided by kilometer squared, how much area of the terrain you used to to accomplish this transmission, and S is how many seconds you used.
That's the question I really want to ask. Why that instead of bit meter per hertz meter squared second?
Because this is metropolitan area networking, not local area networking. That's the only reason.
I was trying to figure out how many megabits.
Use and capacity
Well, yeah, I wanted to show that how much area you use affects your system as well.
to do like limited energy routing and do things directionally just to maximize capacity elsewhere else geographically versus how much of your traffic is multicast in nature, like the inbound and broadcast or
Right.
you go high power and let everybody.
I'm not proposing we do that type of thing on this network. I mean, we all have, there's FM, there's better ways to do broadcasting. This is more isochronous data type application.
Was this unit, was this managed metric something that was in the conversation?
No. I'm just making it up so that we remember this concept because it's very important.
I'm trying to remember.
Yeah, this is because the best way to remember a concept is to have a unit named after a famous person. And that was just the whole idea.
In Philhart's paper from 1990 or 91, I'm sure, had a metric as well.
Well,
I'm trying to remember how it fits into
okay, well, maybe somebody's proposed this already then. Maybe somebody's proposed this already. Oh, okay.
I think he had a different proposal for what he's still trying to win.
No, I don't see him.
Let me ask you a question here. You're getting into the mathematics of this thing. Why don't you just reduce that?
Well, it could be, but I didn't reduce it here so that we were clear where everything came from. Because this all comes from this slide back here.
But one thing to realize is that you intended that first in capital M, capital
Yeah, it should be. No. I got confused here. It should be just bits. Just bits. You got 1 kilobit, and you want to get it from A to B. Payload.
Don't fault an engineer for making a pedagogical effort. Thank you.
Okay. Payload, megabit. TCP/IP is a bidirectional protocol, and we run into this in our this problem. When we started packet radio, you were doing it just with level 2 packet, and when we started to do level 3 and level 4 networking, we quickly learned that these protocols are bidirectional. There's a network level acknowledgement coming back, and that network level acknowledgement is coming back from over the damn horizon. And so every time you try to send your next packet, you're colliding with the network level acknowledgement coming over the horizon. And this type of metropolitan area network has to deal with this because you got a hell of a lot of people in a small space, and it has to work smoothly when these network level acknowledgements are coming back in the range of any particular station. Problems with network level acknowledgements is they're small. They're typically 150 bytes, something like that, which lends to poor packet efficiency in most systems. You cannot bunch a bunch of these things together and get them through because they're going to random destinations from random sources. And so on a satellite system, you might be able to push over, because it all is going into the satellite and out of the satellite, you might be able to time it all so it goes together, but on a randomly distributed network, you have to come up with something better. And they create contention. Contention is the magic word. Contention is how many transmitters in any particular coverage area want to transmit at the same time. The more there are, the less of the throughput. And the technical books are rife with various curves of contention against channel capacity or throughput. And they can be very nonlinear, as we experience on 145.01. The 1 over E, I think, is for CSMA is the contention limited throughput capacity of a CSMA channel. So that's 130% of what the full thing would be, of a broadcast rate of a channel. So we have to handle these things, or else we will just generate this same contention loading limiting problem again. Because the more people want to send, and in 14501 in the CSMA network, the less the channel has capacity to get things through. One ways to handle this is with various types of radios. If you use a full duplex radio, of course it can't interfere. A full duplex radio can listen while it's transmitting, and so if you have a packet coming back from over the horizon, it can listen to that returning packet while it still continues to send its outgoing traffic. That's the best solution to this, I believe. You can do it with half duplex dual radio, where the collisions are avoided until the point of destination. Then you can have collisions with dual. This is two simplex radios. If one radio is transmitting, the receiver on the other one is swamped. But it still can get its data out. But with dual radios, you can get everything back until you get to the point where the packet has to destinate, and if that guy's transmitting, it's not going to get back. You're going to create contention at that point. Half duplex single radio, what we use most of now, is really the worst kind of radio to use for networking. Unless you're going into a hub, and you're never going to transmit to any other stations within the coverage area of a hub, in which case all the packets go up into the hub and all of them come back out of the hub, and you don't have this contention limiting as long as you can avoid transmitting when anybody else in the hub coverage area is transmitting. But that's not the case with simplex radio. Propagation is a very big part of the radio environment. I think we want to use links that are in the Rician regime. Rician regimes, Rice was an engineer who did a lot of work on the two-way or in a point-to-point microwave networks, came up with the thing called the Rician regime. It's a kind of slow-fading statistical, the channel's a slow-fading channel. This can be found on this website here. This guy here is the guy that does the website and does RFSS, I believe is the name of his company. He's a consultant for spread spectrum type like things. This is the type of as you go with distance, this is the received power in DVM versus distance. And this type of graph is typically what you see when you have a small portable station moving away from a much higher single point. This is the hub type propagation situation. I think a lot of the confusion that we've had on the various various email talk groups has been people trying to read the technical side of wireless propagation and concluding that unless we can do it with handhelds, I mean, this is the handheld RF or propagation situation. And what I think for metropolitan area network, I'm not talking handhelds. I'm talking hands at their home QTHs with some kind of station. N equal 2 is the slope of the curve. That means that as you go out in distance, if you double the distance, it's 20 log of factor 2, that's 6 dB. So it's 6 dB per octave slope. N equal 4. This is this is in the Rayleigh statistics. What happens is when you get out beyond a building, a direct line of sight to the main hub, you have basically your signal is got to diffract over an edge of a building down into a street, and also with a portable handheld station, even if you have ground bounce as well. These conspire so that the typical experienced roll-off here is 40 logs. So this is 12 dB per octave. So if you double the distance, you get 12 dB additional loss. This is also the statistics of this channel is very variable. You have multipath is now a significant amplitude with respect to the direct signal, and the signal is all over the place. and in amplitude, and the delay spreads can be large. I mean, you can get behind a building where the direct path is non-existent, and then you could have two reflections coming in, and they interfere very weirdly, and the data gets through, but I mean the signal gets through, but it's not decodable because of delay spread. This is more what I picture the type of radio propagation we should be using. This would be typically two stations on rooftops that are going to clear other rooftops. The ground bounce is minimal because the antennas are focused antennas, and the ground bounce is cluttered up with obstructions anyway. This would be similar to point-to-point type radio system. If your towers are right next to each other, there's no blockage. It pretty much follows free space. But as soon as the antennas start to see the ground, you start to drop down away from free space into diffraction, where there's the ground, the hump of the earth, or the hump of your neighbor's house, is partially within the beam width of your antenna, and so you have an extra loss, which is due to the beam width of the antenna being partially obstructed. Even if it's not a direct obstruction, it can cause a diffraction loss, and that's typically on the order of 20 dB. This slope is still n equals 2, though, but you still have an additional loss. You can start to get around this as you go higher and higher in frequency. The German FlexNet system going valley to valley, where they're pointing 1-watt signals across these valleys with tight beam antennas, the beam never gets down into the valley. It's what's called a first Fresnel path, and the loss of a first Fresnel path is on the order of free space. So that's why they can do with 1 watt what we do with 10 or 20 or 100 in that regard in the U.S. here. So, but eventually you're going to get into a point where the multipath is again a significant factor, or significant signal strength with respect to the direct path, and although you may see large peaks, the average signal will start to go down with an n equal 4 slope, and that's again the Rayleigh statistical regime of signal propagation. But rooftop to rooftop, very short range, I think we can operate in here. And by doing shorter paths, we can, and with directive antennas, we can minimize multipath. But even so, the environment is very random, and we can't all hire propagation engineers to go repoint our antennas for us every change of the season when the leaves grow into the trees or whatever happens. And so some kind of automatic detection of usable paths and reconfiguration of the network is needed, and that's kind of the summary of my propagation thoughts, is that it's just too variable to trust. You can't just point your antennas and think it's going to work all the time. Glenn Engen has this thing called wrote this paper about what's called Hubmaster, where they had a bunch of different antennas pointed at various different locations, and they're able to get around this type of problem by just going with a different path. The FlexNet system is probably the widest deployed amateur radio system that will automatically reuse various paths. So I believe, but I haven't been to Japan, so there may be systems in Japan that are like that. Delay spread is the next main. If we want to do megabaud, delay spread is the next big issue, and it's even an issue for cellular telephone type like systems, especially the GSM system, which operates about 231 kilobits per second. But it's a big, but that's an omni antenna system. But so we'll get into how that affects. Let's go to this is what, if you took a microwave oven transmitter and sent one pulse out of it and then listened to it at various locations within your area, this is what you would see on an oscilloscope. You would see the direct path coming in as a very strong spike, and then you would see the weaker reflections from various multi-path reflectors. This is a big problem for data because when you're receiving this spike, you're also receiving these reflections come in later. So as your data comes in, it's overlapped across these times. So what happens is you get intersymbol interference. When the direct signal comes in, it comes in at this time, and you have a certain bit at that time. But if this is one bit sent independently. Now, if you have a bunch of bits being sent over and over from the previous bits, you have these multipath reflections coming in while this has been received. And so that immediately limits your signal to interference ratio, and it also will distort. And so that so if the bit is different than this bit, it will try to be copied as there will be an ambiguous result in what the bit actually is. And this is what we think we've seen even on our 9600 baud links, and this is caused by reflections, even when the signal is not null by bandwidth. With a wide bandwidth signal, the signal's usually, there's this, well, we'll get into that. Saturation. If you have like K9NG modem can run in 20 dB signal to noise ratio.
Okay.
And
is it determined empirically?
it's well, it's how good your modem is. If you got if a modem that can accept interference that's only 10 dB down, it would be 10 dB. Okay. But most cheap amateur modems, 20 dB is more typical. It's how good your modem can handle interference or noise, the signal to noise ratio of the or signal to interference ratio of the modem. So modem capacity to reject interference. And 20 dB is just a number I picked out of the air for discussion purposes today. That's 100 to 1 in signal amplitude. Okay. Okay, we can also see from the this equation on the bottom here that the maximum delay time is, as defined by that point reflector at the intersection of the minus 13 dB beam width rays, is the maximum delay time is the distance, the direct path, the distance between the two stations, divided by cosine of the bandwidth max, or the beam width max, divided by 2. So from this equation you can see that the bigger the distance between two stations, the bigger time delay max is going to be. So the larger the range, the slower you have to go, because you'll have interference on the next bit. And you can see the narrower the beam width, the faster you can go, because the energy will be scattered, will be attenuated beyond that time. What kind of, well, we now have FHFSS, and that's frequency hop spread spectrum, and direct sequence spread spectrum, and how do these type of spread spectrums perform in a multipath environment? They're better, and here's why. But FHSS is not better in the time domain. Present technology of frequency hop spread spectrum hops at 10 milliseconds. These delay spreads are coming in 2 microseconds, 0.2 of a microsecond, whatever, they're not going to be avoided. If you had a FHSS system that could hop to the next frequency before the reflections came in, then it could avoid the interference caused by the multipath reflections. But the present technology doesn't do that. So it doesn't handle, so delay spread is still a problem for FHSS. In the frequency domain, in the frequency domain, multipath phenomenon looks like there's a time delay for the direct path and some kind of attenuation. There's in the reflected path there's a time for the reflection which is equal to the direct path plus the delay spread, time for the delay spread, and an attenuation of the reflection. Based on the ratio of the times and the amplitudes, the attenuations, you will get a varying patterns of swept frequency, swept amplitude. And typically what you'll see is a notch at one particular frequency. And when I've been talking about wide bandwidth signals here, my definition of a wide bandwidth signal is a signal that's wider than the multipath notch. Now, narrowband signals such as what's used FHSS signaling are not wider than these notches. They're if you got a 50 kilobaud signal, it's maybe 100 kilohertz wide. This notch is about 100 kilohertz wide in some of the frequencies we use. So when the frequency hopping signal comes popping along here, it may fall into one of these notches. And the notches can be variable in amplitude or in frequency, and they're randomly varying in amplitude and frequency, just like FHSS. So it's kind of like a packet. It's kind of like 145.01 where you have a collision, only in this case, instead of a collision between two transmitters, you have a collision between the FHSS signal and a notch in the spectrum, or the frequency response of the spectrum. So you miss a packet every once in a while. That's not so terrible, because if you had a narrowband signal and the null came drifting along and decided to sit on you for an hour, you would be off, your link would be down for an hour. But with FHSS, it's going to drop a packet every now and then and scatter off, and it's not really, you're not really going to see it as a user other than in a slight increase in bit error rate. So how does the direct sequence spread spectrum perform in a multipath environment? In the time domain, the direct sequence spread spectrum can attenuate reflections that occur more than one chip time by the processing gain. So if you're locked on in timing to the direct path, the other paths are going to, if the other paths take more than one chip time, and that's 10 megabaud or 11 megabaud in like a waveland system. So that's pretty quick. And we're down in the microseconds or sub-microseconds being able to throw away the delay spread effects. The energy that is reflected is attenuated by the processing gain when it's not locked onto that main signal. So that's a big advantage for a direct sequence spread spectrum. In the frequency domain, if the signal is wider than the null, that by what I called wide band signal, you have this direct sequence spread spectrum signal. It's kind of like this. So this really only represents an attenuation of the signal because part of the energy is being reflected, but you still have a lot of the energy getting through. And so in the frequency domain, it represents an additional path loss, typically in performance. So DSSS can handle the time domain problem as well, but probably, but because of the additional path loss, again, it looks like an increase in bit error rate. Oops. Okay, if in designing a system, we have to consider interference. And I put this waveland ricochet in here, but he's not here, try to see if we can get to some discussion, because I guess there's a big war going on in Laramie, Wyoming right now between a ricochet, which is a frequency hop spread spectrum cooperative network, and waveland, which people have used as a bridging network in an outdoor environment. The gas company wants to read their meters, but they also want to pay for the equipment they need to read their meters remotely by selling the capacity to various people who would access the internet over it to get email or whatever. But in Laramie, they have a big ongoing network called the Lariat network, which uses wavelands to various high-performance users within Laramie, Wyoming, and apparently these ricochet networks, the ricochet frequency half-spread spectrum things are very cooperative in the way they're not single transmitters. It's a whole network of transmitters, and they all kind of cooperate to make sure things get through. And they're causing all sorts of problems for these wavelands, which are direct sequence spread spectrum type devices. Another problem with interference for this type of network would be weak signal contesting. Believe it or not, there are people up at the microwave bands or 900 megahertz that think that the only purpose for ham radio is to see who has the biggest signal. And they do get on and prove who has the biggest signal every once in a while. They call it a contest. I think our network needs to be able to avoid pointing or using paths that run through weak signal stations. And by having a directive antenna, they will be able to, a path will not work if somebody with a kilowatt comes on and starts radiating all over the place. And so that interference can be detected as a problem, as a path that doesn't work. And consequently, you point your antennas at a path that does work, and that would be away from weak signal stations.
The weak signal receivers, if you have to not transmit, not the weak signal, not the transmitter.
Well, if he transmits, you're not going to point through that path, and his receiver and transmitter at the same location.
Two-way communication. You can't receive the time.
So basically, we can share with weak signal people by the same way we're going to share amongst ourselves with Directivity Division. And basically, we're going to see if you got two neighbors and they normally talk to each other, and then there's a weak signal contest, and the kilowatt comes on, they can't talk over that path again. So now you have the level 3 routing is going to route around it, point the path to other neighbors, and it's going to go around them in a loop. I think whatever type of system we do has to be able to do that.
What about different forms of modulation?
Well,
What happens if we're talking about a CW station?
These types of radios cannot handle are not going to be expensive. The station may be reasonably expensive, but the radio itself can't be, or else it's not going to be economical. And so anybody with a weak signal, 10 watts or whatever, is going to prevent communication between them by overloading the receivers, as if they point down the barrel. So the way to take care of that is to just route around it. So you go out to where the power density is down to half a watt and the interference can be handled, and you come back in. And by going around it, you also avoid interfering with them trying to listen as well. So that's kind of the solution to that, I think. Now that's a pretty controversial statement I just made there. Do we have any discussion on this? But I think this is a way we can handle this, at least in the first pass, first guess way of handling it. Go ahead.
How long do you stay off? If you hear a strong signal on frequency, you're going to stay off it for a while. How long? How do you
Well, packet takes a while to reroute. It depends on how you set your timers. So, I mean, you don't want to set it so that you come back within 5 minutes or something like that. So, that's a network operation type thing.
I want to listen on a frequency, not listen before transmit, not transmit before listening to transmit.
Well, transmit path doesn't work, don't transmit that direction anymore, go somewhere else.
Talking from the point of view of the what we signal at.
All he has to do is transmit, and they're going to run away from him.
That's right.
So it's just like playing with the woodpecker on HF. It's the same thing.
Not only in weak signal work, you listen from your transmit. They hear that when you go in the dial.
So you point your
Stop, and so you
where you want to listen, you key down for 10 seconds, and then what you could do is like do a 360-degree beam sweep with the key down, and then you can listen everywhere. Go ahead. Excuse me?
Waveline is using DSSS.
Waveline is a DSSS system.
What is the process gain?
I believe it's 11 dB.
11 dB, 10.4 or 11 dB?
And the ricochets are on the order of 30 dB. I think they're like 50 kilobaud, and they cover the whole 26 megahertz. So, yeah. Yeah, it's a slow hopping system that covers all of 902 to 928 megahertz. So, which...
Explain to me, I think we're going to end up, if you do that, creating bigger contentions than what's happening in 2 meters right now.
How?
Right now, the ARRL basically put a petition into the FCC, and that's not the proper term, and I realize it, to make the band plan actually part of the regs. So because the FMers are transmitting, they're listening down at the bottom end of the 2 meter band,
well,
they don't hear a thing because they can't hear CW and they can't hear sideband. As far as they're concerned, there are no signals down there.
Well,
As far as their receivers are concerned,
as far as 2 meters and 440 goes, I don't think we have an issue with that. This is a type of system that's going to be up above a gigahertz somewhere.
we're still talking principles here. Frequency doesn't make any difference.
Yeah, it does. I mean, if you say 2 meters is going to be protected because it's a unique user base, I mean, you can always say that 3.3 gigahertz is going to be protected for data because it's the best band for that.
Forget about that I even said 2 meters. What happens if we're at a gigahertz here, and we've got weak signal people, and the only way that we can detect them is by the fact that our throughput goes to pod. Now that
just means we route around them.
Only after we've created the interference.
Well, that's the way HF is. People can't get through, so they go to a different frequency. In this case, stations can't get through, so they go to a different direction.
I can detect signals on HF by listening.
Yeah, but I mean, you still have to transmit to find out if you can make the path. And you have transmitted in the past, and the path works, so you're transmitting again. So, there's got to be, but if you can't get through, I mean, you're not going to be there for a period of time, whatever you set it to be.
Yeah, but I will not transmit over that path if I hear other stations on that path.
Well,
on this one
well, you can think about skip in HF. I mean, if you're on 20 meters and you transmit, how do you know that you're not clobbering somebody? You really don't, because you could be clobbering somebody who's 50 miles away talking to somebody in California when you transmit, and because you can't hear the guy 50 miles away on direct path, but the guy in California hears both of you plenty strong. So you have the same situation. Same situation on HF as this situation.
We'll listen for a while,
and
then he'll ask at the frequency.
And the guy may or may not be a rag chewer. If he's a rag chewer and you listen for a while, what do you set your timer to for how long you're going to listen? This is completely analogous to this situation, how long we're going to set our timing for when we're going to come back to the frequency.
At least I made an attempt to avoid.
Well, in this
particular case, we say we're going to go out there, and if he interferes with me, well, then I'm going to move someplace else. Irregardless of the question of whether I'm interfering with him.
Well, at least you're making an attempt to avoid interfering with him.
After the fact.
But he can always say, please repeat. I mean, he's going to have fading environment anyway.
No, but they're going to make the same thing with you, contention with you.
This is a fundamental problem that really has nothing to do with what this is trying to talk about today. This is the standard problem.
Well, it doesn't if it's a ham radio system.
Well, any kind of listen before transmit system have a problem in the sense that you don't, whether or not you transmit, whether or not you can hear anything doesn't tell you anything about whether or not if you do transmit you're interfering with somebody.
Yeah.
And you have this problem with the metric in that you have, if you hit whatever two systems you have that are trying to play this, it's how you listen whether or not.
I believe on 20 meters there's plenty of people unlike you that use this system that I just outlined right here. They transmit, then somebody says, get the hell off the frequency, and then they move. So there's not much difference.
I think this may be a side benefit of some level from the proposal. I wouldn't sell this as a feature.
Well, no, the system has to do this just to be able to maintain its internal communication. And in order to maintain its internal communication, it has to be able to, as a side thing, to avoid interfering with other people pretty much because their interference is going to disturb their communication. So, anyway, this is kind of like, these are system issues still, not the actual system. Okay, now we actually, how are we going to handle, well, we've talked about how we're going to handle the multipath and multipath situation. And direct sequence spread spectrum, processing gain, and antenna directivity are complementary in avoiding delay spread and other multipath problems. And we'll look at figure 9, how that works. They're basically the same thing. In this thing here. So if you have two stations which have their antennas perfectly pointed at each other, on the minus 3 dB beam width ray, a reflection would come in at minus 6 dB to the distant station. If you added 14 dB of processing gain, you would now have 20 dB over the under the direct path of the reflections that occur at the intersection of the ray, the minus 3 dB rays. So in this type of situation, you can, the reflectors outside of this zone here are going to be attenuated in time, in amplitude by 20 dB because you're using 6 dB you have 6 dB of reflected of antenna directivity attenuation, and you have 14 dB of direct sequence spread spectrum attenuation. So they're kind of a complementary type thing. What you can do is you can design these beam widths so that one chip time, so that this intersection occurs less than the chip time, and so now your one chip time multipath reflectors are outside your beam width, and so that you can protect the direct path perfectly from reflection. And if your beam directions aren't continuously variable, instead of 14 dB of processing gain, you need 26 dB. So that means if you end up having one station pointed such that its minus 3 dB ray just kind of comes underneath the minus 3 dB ray of another station, you no longer have the 6 dB due to the antennas. You need, in fact, the reflection on the other half of the null can be, you need to go up to 26 dB. I should have done a diagram on that, but trust me, it works out. If you want to talk about that later, we can do that. Draw some graph, or you want me to talk about it now? But that's, so if you have an antenna system where the beam widths do not align perfectly, they're not continuously variable, but you still are within the 3 dB beam width station to station, in order to get a 20 dB guarantee of reflection attenuation, you need 26 dB of processing gain. Now we're going to talk about Directivity Division Multiple Access. All this has been building up to how we can, what kind of radio system we can build to, and why we want to do it, how we can do it, and this is what I think, based on all that previous information, what we can do sometime way off in the future. I call it Directivity Division Multiple Access, WAN for metropolitan area networks. WAN stands for wide area networking, and we'll get into that. Each direction from a site can be each direction is a separate channel. You do this with an azimuthally rapidly scanning antenna and say something with under a millisecond random access time. You can go from any direction under a millisecond. This is kind of how we would do it. The capital letters is the transmit code. So if the guy is transmitting down this bearing on this beam, he would transmit with code C. And the little letter is the receiving code. So over here, this guy listening on the reverse bearing is listening with code C, and vice versa. And you can see how this all works out. And there's advantages of doing it this way.
What is the code?
It's the spread spectrum spreading code. By having the reverse, we'll go through the various interference possibilities here. This guy is transmitting with code G. This guy is transmitting is receiving with code G, because he's listening to this guy who's transmitting with code G. So both of these guys are on the same code, and they're neighbors. So you have to get 20 dB front-to-back ratio out of your antennas. Well, actually, it has to be 10 dB front-to-back ratio, 20 dB total isolation. But these antennas here easily handle 20 dB front-to-back ratio. So this is actually, with those antennas, this is going to be 40 dB plus the path loss. Well, that's the ratio. Well, assuming these are all equally sped, the interference from this transmitter on this would be 40 dB down than the signal from this guy down there in the corner. So those are direct neighbors. Now, if they're closer together, with this antenna, they could be 10 times closer together than the one they're trying to receive, because you got extra 20 dB of total isolation in antennas such as this, which we'll get into. You want to go back to that? Yeah, these two can be closer together by 20 dB and attenuation. That's so the front-to-back ratio has to be greater than 20 dB. With an antenna that has a 20 dB front-to-back ratio, so we end up with 40 dB if they're equally spaced. So that means you can bring these in by a factor of 10 to the 20 over. I'd have to work it out, but they can be considerably closer together because you have that much additional performance in the antenna. Now, if you have, we're trying, when you have stations that are using paths which cross, this is where this spreading code really is advantageous. This guy's transmitting with B, this guy's receiving with B. Now, if they were all using the same spreading code, with this path coming in here, and if you had some reflectors in here in this scattering volume, they would copy and interfere. But by using different spreading codes, the reflections are going to be attenuated by the processing gain. And so this guy's going to be able to get through to this guy, even though there's reflections in this scattering zone, because this guy up here is transmitting with H, and this guy's transmitting with B, and the receiver is listening with B. And so that's one reason why you want to use spread spectrum besides directivity in such a network. If you look at this is where we had a hub using the whole volume of the area there to transmit to one station. Now we have these two little areas here being used for two communications, not only just the whole big hub for that little tiny communication. So you can see the area the area efficiency advantages of something like this. I mean, this area here, outlined by the triangles of the beams of the rays, is the area required to handle, to provide communications for 4 users, versus a huge diameter required to handle from the hub to one of the users. And this is a big advantage of the system. Okay. That last diagram showed that the crossing paths were isolated when they're on, because they're on different beam bearings, and the different beam bearings are using different codes and direct and antenna beams. We also need to use power control direct sequence spread spectrum. One more. All right, and this is the problem with this system, is when you have 2 paths in lines of immediate these are all immediate neighbors, and on average the distance between each one is going to be the same. This guy here is transmitting with code D to station 2, who's listening with code code 2, and the power is set so that he gets 20 dB signal noise ratio. Station 2 gets 20 dB signal noise ratio. Now, station 4 down here wants to listen to station 3, and since they're on the same bearing, they're all using the same spreading code. Station 4 is listening on code D, and station 1 is transmitting on code D. And they're all on the same bearing, so the signal from station 1 is going to get into station 4. In the meantime, station 3 is trying to transmit a signal to station 4 using code D. And so on average, the stations are spread apart evenly, and if there's Rician paths, and this is spelled Rician paths between all these different stations, the power ratio at station 4 the power ratio of 1 at station 4 to power of station 3 at station 4 is only going to be 9.5 dB. That's going to be very difficult to copy. But I mean, hopefully we don't always do that. But in many cases, what's going to happen is since these stations are all in a line, they're maximally spread apart, and so hopefully the signal path from station 1 to station 4 will start to drop down into the Rayleigh regime, which has an n equals 4, if you remember from our our previous plot, the figure, in which case the ratio of the power 1 at 4 to P at 4 is going to be 40 log 1/3, and that's minus 19 dB, and maybe it'll work because it's close to 20. But there is a weak point in that situation. Somebody can come up with a better scheme. But hopefully all these crossing paths being able to use the same volume will make up for this. Does anybody want to talk? This is kind of the gist of the concept here in these 3 diagrams.
Spread spectrum,
It's both spread spectrum and antennas. That's true too. I mean, if you use a different time, if you added a time base in at each station and used a pseudo-random pick for each transmission of when you start the chips, you could then have a pseudo-random reduction in probability of interference by like a P persistence type like thing. So that might be one way to handle it.
The code that is selected always fixed to a certain direction.
Yes, that makes each direction a channel. That's the concept of making it a channel. So in this particular case, the capital letter D here is the transmitting code, and it listens. When it listens with code H.
Every node in the network.
Yes. And see, that's kind of the idea of infrastructureless. You make each station has more capacity, and what you use the capacity for is being able to get all these packets around for everybody else without having to have an infrastructure. But that's a lot. This is kind of the minimum I think each station would have to be able to to make a network like this. It's a considerably much more expensive thing than a TAPR TNC1 or 2. Because
requires a certain amount of cooperative orthogonality in all the codes as well.
well, that's programmed into the radio. You buy it. I mean, it requires cooperation by the engineers when they make them. It doesn't require cooperation by the operators.
Well, true.
Like the antenna orientation installation.
Yeah, so you have to find true north. Yeah.
Have you thought about what kind of codes and companies would be available that you want to use?
No, I'm not a spread spectrum expert. I'm more of an architect type person. But I believe there are. But I looked at the antenna side of this, and then when we started thinking about this, I think it was like 2 or 3 years ago, I latched on to something I could do in this future, and that is the antennas, and we'll talk about that eventually. So, but this is this kind of generated when there was 3 of us, Karn, with the guy from L.A., Rich, I can't remember his name. There was Dr. Rich from England, and then there was Mike from L.A., who's done 9600 baud stuff, and we were all, well, it's Dwayne's fault. We were at the Texas symposium, and Dwayne challenged us to do something that the commercial people would blow the commercial people out of the water. And so this is kind of what stuck in my mind is what we could do, and this was in the spring after that. And we were all having this big hash session on the email, and somebody mentioned the word flying saucer, and I said, well, this would be like a flying saucer network, because each of these antennas would be like a donut up on your house. And it would be scanned, and then that's when I coined the phrase Directivity Division Multiple Access. And but I'm not responsible for all the ideas. I'm just trying to disseminate them. So this is kind of the idea. I mean, if you go up high enough in frequency, the antennas become cheap, and duplexing becomes cheap. And there's a possibility, and you can also get wider bandwidth. So it kind of all is. It's kind of it's slewing all the way to the opposite way of all the variables slew the opposite side of the way we've done things in the past. Go ahead.
As a practical matter, doesn't this require a fairly high density of users?
Well,
much more suited for metro area than
yes,
rural or more
yes, I agree. And the way I kind of envision it is 2 guys would set these things up, and they would talk to each other. But of course, the true power of it wouldn't really occur until, say, maybe they got a friend to try it, and he got on there. Just like 14501 grew, instead of you start out with something that when it's fully populated, it still has a chance at working versus something that people just kind of abandoned.
Wondering, real world system, is the idea here to be able to have enough isolation between these channels, not to actually utilize
Well,
direction simultaneously from one location?
yeah, with the
Getting out the back door and stopping somebody out in the east.
well, back to back, it's no problem, and we do this on weak signal 2 meters all the time because the antennas have on the order of 20 dB front to back ratio. That makes 40 dB isolation. So that's enough if you're trying to receive a signal that's equally powered with power control. It's equal power to what you're being interfered with, and then you can isolate with 40 dB. You're going to have 40 dB signal interference ratio, and a lot of modems will work with 40 dB signal noise ratio. They'll even work down to 20 dB signal to noise ratio, I believe, and that's why I have 20 dB up there on that slide right there. And in this situation, the reflection is hopefully going to be somewhat attenuated. So besides the processing gain, you also have the radar cross-section loss. The radar cross-section is an R to the 4th type factor, so it has a chance.
So the idea is to have a lot of stations that can talk to each other pairwise in sequence, but not interfere with.
Well, that gets into accessing the channel, which I'm going to talk about in a little bit in the future here.
The overall design, you want these stations, at least adjacent stations, to be able to talk to each other, but you don't want all the other guys.
Yeah, right. That gets into, I mean, I'll get into why you want to do that. That's called minimum energy routing, and it's been pretty much accepted for these, like the ricochet network and these type of, any kind of networking environment, that networking station where it's a large of randomly distributed users all using their own resources for talking to each other, infrastructureless in general.
So this kind of networking has been done in the ricochet type of...
Well, not in the directive pattern where you actually use directivity, you match spread spectrum processing gain with directivities to make channels out of the directions versus directions by themselves. You're taking each direction and you're turning it into a channel, a full bandwidth channel, so that you don't have to have different frequency channels, you just have different directions. Let's see. Which one?
Right here. What happens if, the way you've drawn it there, you got to say that the station 1 was, from the point of view of station 4, station 1 is 3 times as far away.
Right, on average. I know.
What if you had, I mean,
what if station 2 and 3 are real close together?
Or even soft places. Station 1's trying to transmit to station 3 and station 3 is trying to transmit to station 4.
Well, that's another reason for using minimum energy routing.
So you will go multiple.
To minimize contention, because if you have station 1 transmit, station 3 and station 2 wants to transmit, you have contention. When you have contention, your channel capacity goes down.
Yeah, I thought of the question before you actually got to that.
Okay.
Just
Yep.
yeah.
So this gets into the wide area networking structure. You want to communicate to the closest neighbor station. This is called minimum energy routing, and it provides a method of minimizing the amount of area that's covered to achieve a certain communication. And since we're using power control, that results in minimum energy. Here's an example of what, how much energy it takes to go from 1 to 4 with 3 hops. How much area? Area and energy are the same in this type of scenario. Station 1 wants to talk to Station 4. They can do it via 2 and 3 via 2 hops. And this triangle here represents a 20 dB signal-to-noise ratio power level. That area is occupied with 20 dB or better signal-noise ratio from Station 1 transmitting to Station 2. And again, this triangle is Station 2 to Station 3, and again, Station 3 to Station 4 and back. So basically, you can look at this as one big, long box that has 3W plus the distance from 4 to 1 in area, W being the width. Now, if you want to do 3 hops, you want to do the Station 1 to Station 4 as 1 hop, you end up having to increase your power. And so the area covered is over here on the right-hand side. Is the W ends up being 3 times as wide, because now you have 3 times, well, you have, I'm not sure if I got my logarithms right, but you end up with 3 times the power, and that means 3 times the area, and that's 3 times the area to do this same communication as over here when you do it in multiple little hops. Consequently, there's 3 times as much other communication that can be going on at the same time. A whole bunch of guys over here and a whole bunch of guys over here, if you confine the packet to only go to the nearest neighbor here. And that means contention is at the absolute minimum for the network. That means the capacity of the network on a whole is at the maximum level. You can't get any more out of it because these guys here are not trying to overlap you, and so it just kind of works like that. Now this is more like a suburban type scenario. I'm sure in a highly dense type urban scenario there's going to be people overhopping other people because they just don't know they're there. but that's kind of the idea. I got my logarithms wrong on this. I just realized this. This 3 may be a factor of something else, but it because I still have to think about that one. You think this is right?
No, the 9.
The 9's right? So, but there is a dramatically larger area occupied when you make hops bigger. And this is why you want to use minimum energy routing. And this works for circles too. And there have been professional papers written up. In fact, one of the, Tim Shepard, I guess he's going to present his paper, his doctoral thesis, which goes into very much mathematical detail about this very problem. So I'm supposed to be warming you guys up, I guess. But he's doing it with circles, not triangles. So this type of minimum energy routing is what is key to doing a graceful sharing of the resource between all users. Consequently, since you're doing the shortest hop, if you're doing a hop that's 1/3 as long, you want it to go 3 times as fast, right? Because in the end, you want the transfer to occur in the same amount of time. Using the entire bandwidth allows for maximum baud rate when you're going directive. That means the minimum time per packet. And the antenna directivity required to allow delay spread to be overcome reliably when it's broad bandwidth is that you need antenna directivity to do that. I've just laid out a circular argument, and they all go head to tail, which is very exciting for a network architect. And what you got is circular requirements. Directivity is needed to reuse the band. To reuse the band, you need minimum energy routing. To reuse time, you need minimum energy routing. To minimum energy routing implies the highest baud rate possible, and highest baud rate possible implies directivity to get through delay spread. And now we got a nice big circle. And that's the aha syndrome when I'm looking at this stuff. So it all kind of goes in a big loop. And so we've all taken all the variables and all gone off to one side from where we started. And any comments on this one?
What about switching times at each node?
Well, that gets into the modem stuff, but I'll get into that. Because the reason we don't do this in the past, so I'll get, it's on a slide coming up. Delay spread, 1 megabaud data rate. If you fix it completely by direct sequence spread spectrum processing gain, you need 20 dB of processing gain. That means 100 times the bandwidth. Now, if you want to do a megabaud, it means 100 megahertz. There are bands we have 100 megahertz on, but there are no IF chips, at least not in the United States that I know of, that will do 100 megahertz bandwidth and then D to A converters. At least they won't do them cheaply. I mean, maybe the CIA has them. I don't. So if we fix everything by direct sequence spread spectrum, the economy just gets blown out of the water. If we fix it completely by directivity, if you have a 20 dB, you want to get 20 dB direct path at 1 mile for 0.2 nanoseconds. That means you have to have a 60. So at the intersection of the minus 13 dB point, or the minus 13 dB points, or yeah, well, this should be 26. Anyway, remember that other slide where I showed the minus 13 dB points in? You need to have a 60-meter path length difference. That represents 60 meters, and free space represents 0.2 nanoseconds. And so for 26 dB beam width, that gives you the 29 the 60 meters results in 20 degree beam width, and that's got to be at really the minus 13 dB point of the antenna, not the minus 10th. And so this becomes one hell of an antenna, because I mean it needs a if the 29-degree beam width is at the minus 13th point, well, the minus 3 dB is going to be down there, maybe 10 times smaller, or a little bit wider than that, and that's going to be a really large antenna and expensive. It means you even have to go either higher in frequency to a point where it becomes expensive as well. So, but if you use a 14 dB processing gain, direct sequence spread spectrum, and directivity, that 29-degree beam width now can be your minus 3 dB point of the antenna. Now, that's not a hard antenna to make. I can make one of those. 14 dB processing gain only requires 25 times the beam width or bandwidth, and that's right on the edge of economical right now. So that's something that's practical. So let's look at technologies in the radio vein that we might be able to do something like this. Wavelands and similar type-like devices, there's a very popular chip called the STEL-2000A. Zilog makes a version of this. There are Stanford Research, I believe, came up with it. It's a digital match filter, direct sequence spread spectrum. A digital match filter is a way of decoding spread spectrum where you slide two data signals across each other and compare them all simultaneously. You have each little time domain bucket, and they're all being summed out simultaneously. When the alignment occurs, you get the decoded signal out of the sum side of this type of device, and it can be done it originally was done by the military with surface acoustic wave devices, but now it's done in this STEL-2000A. It's a 64 bucket digital match filter, which means it can have a processing gain up to 18 dB. Now, if you wanted to do this if you wanted a 20 dB, you would need 100 bit buckets. If you wanted 30, you would need 1,000 buckets. Now, that's an awful lot of real estate and a very expensive chip. And the other thing that we have technology-wise is the 100 kilobaud FHSS radio. Because this digital match filter is comparing these things on the chip cycle, and there's usually how many ever chips that refers to the processing gain per symbol. These things will lock up in typically one symbol time, which is why they were picked out for the waveland type thing, where they were very interested in having very quick lockup times and not wasting a lot of time. So if you had a GP of 10, you would have 10 chips, and so for each 10 chips, you would have one symbol. So the symbol is made equal to the number of the processing factor times the symbol time. So this answers your question. How do you bring the antenna on and lock up so rapidly? Well, this chip, the digital match filter direct sequence spread spectrum, can do that. At least that's what it says in there. Now, a lot of people give me incredulous remarks about this, but I've called up their application engineer, and they confirm what it says in their literature. And it's basically because it's a digital match filter. It's comparing all these different phases simultaneously by sliding all these signals, or a large swath of each signal, the code and the incoming signal across each other simultaneously each chip cycle. Does anybody, please, if you know better than me on this, please comment, because I'm interested to know.
This question is not necessarily on the topic of the slide, but it's just sort of all boxing together. I think you based a lot of your analysis on the concern about the delay spread.
Yes.
To get the multi-path interference in the time domain to be down far enough to mess up the norm. But you've also thrown in spread spectrum versus spread spectrum.
Well, because it's not economical to do it both, to do the whole job with one technology or the other. But if you put them together, it becomes much more economical.
The actually spectrum is going to have an ability to reject
Yes.
multipath.
Right. Right. So
you still need the same multipath rejection on the split spectrum.
Oops, better check this. If you have a 14 dB spread spectrum processing gain, you're still going to have, it's going to be attenuated somewhat, but you're still going, you need the directivity for more than spread, for delay spread. You need it for sharing as well. But you need that goes back to the circular thing, the circular argument thing. They're all kind of, you need various things, each thing for two things, and that makes the circle.
You were still trying to get that 20 dB.
Right, that's kind of a magic number.
And that's what I'm realizing.
Some modems.
I realize a lot of modems need that. The new radio you're building is going to have 13 dB of direct sequence, a processing gain of direct sequence.
That's a number for the sake of argument. Now, if you end up with a modem that needs 9 dB.
Or 5 or 3. Forward error correction is not going to fix delay spread. Because it's not a symbol that's that's 50-50. It's every symbol that's 50-50 when you have delay spread. So because you're interfering with yourself, and it doesn't matter if you increase your power or not, because you just increase the signal that's interfering with you, your very own signal. And yeah, but the delay spread environment may not happen 100% of the time, but when it does happen, every single bit is interfered with.
How much could you reduce that type of multipath problem with, say, circular polarizing?
Well, typically 10 dB. It depends on, it depends. The antennas in space, it depends on the type of antenna dramatically. There are people who have spent a lifetime designing these feed horns for space applications that 30, 40 dB separation between orthogonal polarizations. And if you're out in outer space and there's no birds flying by, and they do this with space-based communications, they point the thing up in the air. They don't have hardly any multipath except for maybe the occasional airplane, and by having a very narrow beam width, the occasional airplane is very far in between. And you have a very controlled RF environment, the dish itself, and then it goes out into it goes out into the beyond the near field of the antenna, and you have a very controlled near field. You can get very high orthogonalities, but right, and then they're probably getting 50 dB. Yeah. So, but in the terrestrial environment, what happens is the currents will flow on a conductor, and a conductor may turn a corner. And so if you're doing vertical to the horizontal, now you've got current that was from your vertical polarization flowing in a horizontal member and re-radiating. Right. And so that kind of screws that up in a terrestrial environment. I've heard in terrestrial environment you can count on 10 dB.
But 10 dB might go a long way for exactly the pressure.
So that means you can use a wider antenna, but it becomes. It doesn't what?
Doesn't change the principle.
Doesn't change the principle. It's more of an engineering issue, and makes the antenna cheaper, or it makes the processing gain less. Or I would prefer to have it make the processing gain less, because you still need to share the spectrum, and the spectrum needs the directivity. You still need to share the resource, and the tighter you make that beam, the better you share your resource, and the lower your contention is going to be. But it makes the antenna more expensive anyway. it makes it smaller, but it still makes it more expensive because now you have the CP feed arrangement, which is very difficult. It's not difficult to engineer, but it can make antenna design, it can make it more expensive, especially with an antenna like this. Like this antenna here, it's easy to make in a high gain antenna like this, which is just a big patch, has wide beam width, but if you make this CP, you're stuck with half-wave patches. Half-wave patches have much narrower beam width or bandwidth, and you need more of them then. So it makes it, the antenna, even though it makes the antenna smaller, it doesn't necessarily make it more economical.
The economic issue is design cost?
Well, that's what we were talking about. You could use right or circular polarization to reduce costs. So.
When you think about circular polarization, your stations that you're potentially interfering with are going to be using the same polarization.
If they, yeah, you see, yeah.
Reflections reverse it.
Right. So if you're trying to listen on right hand, the reflection will be left hand.
Okay.
So if you transmit to right hand, listen on right hand, the reflections are left hand, they're down in the mud.
So the double reflections come back the same polarization.
But you can't use CP for directivity type purposes because there's only two CPs, right hand, left hand. Right. So where with spreading, there's as many as you want, really. The HFSS radios, because they're frequency hopping, they can use correlated modems. They use GFSK modems, all of the K9NG. The K9NG typically locks up in 100 symbols. But there has been a lot of work on this, and they basically can transmit these 50 kilobaud packets in about 10 milliseconds, I guess. And I'm not, but you have a Gaussian filtered frequency shift keying, and that's the modem that's was used originally on the first biggest application of it was the analog cellular telephone data channel. That was the first one, and K9NG worked on those, and so that's why he knew about it, and so he made a ham radio version. So. And you're basically getting a lockup of 100 symbols, although this is very susceptible to engineering. But typically, in my experience, they lock up in 100 symbols. Another new technology as far as radios that's come along is the 1 to 10 megabaud multi-tone modem, discrete wavelet modulation, this type of thing. It's used for ADSL, asymmetrical digital subscriber loop. It's basically a wireline modem. It has long training times, but because it's a 10 megabaud version of a Clover modem or something along that vein, it has very good delay spread protection because it's signaling at maybe 9600 baud. But the aggregate modem has 10 megabaud. So this is a possibility for doing things, although it's a ways off. I think it has long training times because it's mainly intended for wireline purposes. I'm not sure on that, but that's what would be my belief. Or any kind of wireline modem would have all very long training times because they have all night to lock up. And then they just stay locked up. Does anybody know different or want to comment on that? That's kind of a weak point. Okay. Another technologies that have come along is the antenna system technology since we started packet radio. The duplexers in particular are now amazingly cheap. You can buy ceramic TEM mode duplexers from Murata, from you name it. Little tiny things. There's like 5 or 6 little coaxial resonators in these things. And every time you pick up a cell phone, there's something in the back of it that's doing this. It's one of these little, because you're talking full duplex in most of these little cell phones, and you're transmitting and receiving at the same time. That's a full duplex handset. And the way they do it is these little ceramic duplexers. They're basically ceramic-loaded TEM mode duplexing technology. Because of cellular, in the ham radio side of things, the 5 gigahertz, but at 10 gigahertz, a duplexer that would stay within the ham band would not be all that big, although it might be a little bit tough to manufacture. And new on the scene, there's going to be LC duplexers in cellular telephones in the near future. And there's a new C material for the capacitors that you can, it's temperature stable and very high Q, like on the order 2,000 or something like that. And they're going to be able to etch inductors on there, distributed capacitance, and they're going to reduce the size of the cell phone duplexer at least by half. And this has just happened this year. So that's a possibility too. Duplexers isn't as bad as it seems above 1 gigahertz, and with these technologies that have happened since the start of packet radio in 1985. Another thing that's happened is gallium arsenide switches. You can typically handle a watt with less than 1 millisecond switching. So the concept of a scanning antenna with switching between a bunch of different beam widths isn't all that scary anymore, because you can buy these things for a couple bucks. And they're mass produced and they're all over the place. Another thing that has not really happened since 1985 was here all along, but the development effort has been dramatic, and every cellular telephone antenna now that's being installed is a microstrip patch antenna or something similar. And the reasons for that is that the very low element-to-element coupling. So you can do a Nike antenna array. You can just do it. Just put them all together, and they won't couple, and you won't have to worry about mutual impedances that much. And you can make array of antennas. Ooh, what happened to that thing? Anyway, this is what a microstrip antenna looks like. There's a conducting ground plane. By the way, these were invented in my alma mater, University of Illinois, Champaign-Urbana, as well as the log periodic dipole array. I think almost by the same guy. I think the guy who invented this was the professor of the guys who did the LPDA or something like this. And his name was Deschamps. I only met him once. He was the grand old man. Basically, this is how the microstrip patch antenna works. This is on the order of a 20th of a wavelength. The separation here is a dielectric slab. Typically, a dielectric slab covers the whole ground plane, but I've removed it for the sake of clarity here. On top of the dielectric slab is a patch of conductor, and you feed it. You can feed it with a probe. There's a variety of other patented feeding methods, and you can run into problems if you try anything but a probe, patent-wise. Feeding it with a probe in this place, the unique thing about the microstrip patch radiator is that it's orthogonal compared to other radiators. Other radiators, like a dipole, the resonance occurs in the same length as the radiation, in the same axis. In this antenna, these edges are resonant. They're half wavelength long and half wave patch, but these edges down here do the radiating, which makes it difficult for a ham to build one easily, but makes it so much nicer if you're professional and you want to do various things, because that means you can tweak things at the same time to get a good feed point impedance. But as far as it makes it easier if you want to make arrays. You can make them a half wavelength long and put them side by side, and then this is the array here, and then you can tweak the frequency. Now you don't have to readjust all the arrays because you haven't changed the radiating edge length. If you had half-wave dipoles and you wanted to bring them into resonance, and you might need to squeeze them a little bit, the microstrip patch makes antenna designers' life much easier, although it takes some practice to do it. These radiation edges create E-fields to the ground plane. Now, since this is a half wavelength long, it's something like this. You know, it's a sinusoidal voltage distribution. So this is like a negative voltage, and this is like a positive voltage. and you have, I have the arrows in the wrong direction, but the E field goes to the ground plane or from the ground plane. And if you look on it on edge, the arrows are canceling each other. But if you look on it broadside, that arrow's pointing up and that arrow's pointing up. That means both those arrows are adding in phase the radiation from them. And so you get a nice unidirectional pattern. Typically it's like 90 by 80 degrees for a half wavelength patch that's not a half wavelength patch that's a little less wider than half wavelength. You can size it any, you can make a square patch. This antenna here originally started out to be a square patch, but the patch ended up being narrower to fit it in this form factor. Okay, this patch here, this is the half wavelength in this antenna. And this antenna here, which is on 1.2 gigs, and this is on 440, the patch is this way, and that's the half wavelength direction, but it's long. So it has very long radiation edges, and so it has much higher gain. And so
the thing that, when the feed point breaks the symmetry, where you place the feed point?
Well, that just gets the energy in there. Or you could feed it down here as well. You could put a pseudo feed point with a quarter wave stub there. It wouldn't affect the radiation. Because it's a half wavelength long. It's like a J-pole, only you're tapping off you're on a half wave radiator, and you're tapping up from the shorted edge. Only in this case you're tapping in from an open edge. Kind of like that, not quite. But I mean, if you had a half wavelength antenna and you brought a point up to the side of it to feed it, that's the similar type of thing to this, only this is laid down flat and that's in line.
So how do you rotate?
Well, you build a lot of them and you just switch between them. But there's more to it than that, of course.
These, they rotate perpendicular to the edges there, so you stack them?
Well,
Some stack like this?
this one has its maximum gain like this, so you could just add another one over here and then switch between it.
Okay.
And then
Lay them in a
big circle.
Okay.
Or you can go half wave. This would be, if you wanted to do, this would be vertically polarized if you wanted to do that. But if you wanted to do horizontally polarized, you might stick a whole bunch of them side by side and have a network out here which would phase. And then the switches would control the phasing network. That's another way. Typically you can do 5 beams with 8 elements. Theoretically you can do more, but you do start to get coupling, and the beam amplitude starts to drop down beyond the 5 beams. So the idea I kind of had for the antenna was something like that. With if you wanted to do with something with 30 beams, would be like 5 panels, each panel, or 6 panels, each panel doing 5 beams. And then you would just have a little switching thing that you do. Now it's expensive, I admit, but it still needs to be developed too to some extent. But I mean, if we're going to share spectrum, we got to do something. And this is kind of.
Could these be done on a printed circuit board?
Yes, well, the back of these antennas is printed circuit board, although these are not printed arrays. I'm not going to get too much into it. They are typically done on printed circuit board, but those antennas are usually low in efficiency if you do it on printed circuit board itself. There are other materials out there that help improve efficiency dramatically, and that's why this is enclosed. Anyway. So you got to know what you're doing, but once you know it, it's not that tough. The high dielectric constant materials are not the best materials for microstrip antennas, and that's where a lot of the naysaying talk was in regards to it. The materials had to catch up to the antenna technology, and they have now because of cellular telephone. So So the advantage, they have very high front-to-back ratio. That antenna there, that's the 440 antenna. I had a J-pole across the room. I was trying to do packet 9600 baud. It was about 9-10 feet away from my computer screen. 25 watts on 440. Computer screen would shrink to half. It transmitted literally to half, and that was with me between the computer screen and the antenna, and so I didn't like that either. So also it was a multimedia computer, and so it would make a big hissing sound out of the speakers whenever it transmitted. So that was no fun either. So I put this antenna up here, and there's nary a wiggle on the screen, and so that has about a 20 dB front-to-back ratio. And usually it's better at the center of the frequencies, at the center of the frequency band, and then drops off to about 20 dB at the band edges. That antenna goes 435 to 450 with a better than 2-to-1 VSWR. So that's a typical microstrip patch antenna, half wave. You get unidirectionality for free. Those edges are acting like slots, but if you made a slot antenna, it would radiate in both directions. With this type of antenna, very similar mechanically and cost-wise to a slot antenna, except it's unidirectional now. That's an extra 3 dB of performance. A single half-wave patch is typically equivalent to a 2x2 Yagi. That is the top. This would be equivalent to a 2-element Yagi, and this would be equivalent to a 2-element Yagi fed with the proper spacing to combine the gain, to get the gain. So if you had two 2-element Yagis, that's equivalent. So these antennas, the half-wave patch is like a 6 dB gain over dipole antenna typically, in that range. They're printable, and especially printable at higher frequencies. It's kind of hard to print the patches in those antennas, but another thing with these is they're backwards from Yagis and a lot of other antennas. The bigger the patch in terms of wavelengths, the bigger the bandwidth. That antenna there is like 3% bandwidth or something like that. This antenna here is like 6% bandwidth. It covers the whole 1.2 gig band. It's a half wavelength high patch, but the patch is much longer, and in terms of wavelength. And that makes it a much greater gain and bandwidth at the same time, opposite of Yagi's, which makes it ideal for spread spectrum. And which is one of the reasons why I want a lot of 1.9 gigahertz cellular PCS antennas or microstrip patches. Another thing that's happened is we can now do FEC in real time with the various processors, and Phil isn't here to comment on that, so I'll just leave it at that. GPS, possibly we got 1 pulse per second outputs. We can have a randomly distributed timing source that's accurate to 1 microsecond, 1 pulse. Am I right on that? I need to double check that one. But I believe that's the case with these GPS. Tom Clark's totally accurate clock. Anywhere you are, you get a 1 pulse per second. It's not only accurate to 1 pulse per second, but that second occurs on the second, within a microsecond. So these technologies lead us to how we might be able to do acquisition. You got all these stations, and they're all pointing their antennas all over, just like 2-meter weak signal guys, and not making many contacts because they don't know where each other are. And they can't hear each other because when the antennas aren't pointed at each other, they can't hear each other. So how do these stations all detect each other? The one thing that came to my mind when I first was thinking about this was we could do this asynchronously with full duplex radios. Here's an example of how the acquisition might occur. All stations scan 360 degrees continuously unless they're busy listening. And the accessing station might send a PRBS, a pseudo-random bit sequence, towards the direction of the station that he wants to communicate with. The stations is known already. That has to kind of like, the first station has to be pre-programmed in, and then the networking software has to keep a table of what stations are where, etc. But these stations all know where they are. The problem isn't knowing where they are. The problem is getting organized communication to happen between them. So the accessing station sends its PRBS on the request to send band. It's full duplex. So one band is a request to send band, and another band is a clear to send band. So instead of like an RS-232 having a request to send wire and a clear to send wire, we have actual frequency bands that are request to send and clear to send. The node station detects the within, he's scanning around, maybe spending a millisecond at each direction. So within 360 milliseconds, if he's not busy, he's going to fall on this RTS band transmission. And what he needs to do is then echo that pseudo-random bit sequence. That can be used by the routing software to get a channel statistic. And then he needs to respond with the bit error rate that he's actually hearing and the signal strength he's hearing and his ID. And then the communication can go. And this can happen really rapidly. 360, that, and maybe we can switch from direction to direction faster than a millisecond. Or we have 30, if we have 30 beams, that's 30 milliseconds. So that's another, and so it can happen real quick. But this is kind of the penalty for having a band that you're not contention limited with and can't get anything through. So that's, well, let's go back. Any ideas on it?
I've got a question on the geometry. They're all picking the timing up from the same place.
Well, this is asynchronous. They don't need timing. I'll get to the synchronous idea next. But,
okay.
So this is all, they're just all, whenever he wants to, he gets out there and transmits. And then the other guy comes back to him, they do their...
But as these antennas are rotating, they're all pointing north at the same time.
Not necessarily. No, it doesn't matter. This guy, if he wants to access his neighbor station, he sits on one direction and transmits continuously until the other guy comes around and answers. Okay. Any more ideas on this, or does anybody like this idea or not like this idea? Or, because it's so fast, I mean, the weak signal type like situation, you got 1 minute. In this station, in this situation, you got 30 milliseconds to scan around. So a lot can happen. A lot more can happen. So that was the one that came to mind, and that's the one I like. But I'm sure there's also a synchronous way to do this, and any kind of synchronous method would require a distributed timing standard. And when I read about Tom Clark's totally accurate clock, it seems like, oh, that's it. But maybe this could be Loran C or something else, if they don't turn the thing off. But it could be a computer program and a FM broadcast station, and each using the zero crossings of the FM signal. But how do you get to the right zero crossing for your location? That becomes difficult. But GPS supposedly solves all this, and because it is such high production, it's an economical grasp of stations that might use it in ham radio. That's an example of what you can do with elaborate technologies. If only you can get your production levels up. You can do GPS. We can do DDMA, but only if we get our production levels up. Then you can use simplex radios, and you could have a scheduled scheme. The first slot of the cycle, 1 talks to 2, 3 to 4, 5 to 6, 7 to 8. And maybe the second slot of the cycle, they arrange a schedule so that 2 talks to 3, 4 to 5, 7 to 6, 8 to 1, etc. And you might even have a scheme where maybe I got all this traffic, I need 2 slots, so they agree to go for 2 slots. And the other guy in the meantime tells the other neighbors, I'm going to be gone for 2 slots, and expect me on slot 3, or slot 4, or slot 5. And how many slots per cycle would be the maximum number of neighbors? And of course the maximum number of neighbors in minimum energy routing is the number of directions. So that's the type of thing. This is seems a little bit more inefficient than the asynchronous technique, but it would have to be modeled to be sure, because you have slots you have the maximum number of neighbors being the number of directions. You might have slots that might go unused. And there's overhead there that you don't have in the asynchronous scheme, but the asynchronous scheme you got overhead in acquiring. So, because you know when 1 second is, you know when 2 seconds is, you know when 2.00010 to the minus 6 seconds is. So with this type of thing, you can really divide up a second into the microsecond level. You're using, that's a million, you know, so if you have a million bits, I mean, you have a lot of time to do stuff. Any comments on this scheme? I'm sure there's other ways to do this. This is about as far as I've taken the idea. In fact, I don't have another slide. So now is chat time. I really haven't written up a really good conclusion on all this. I think that this is something to look at. I think that eventually the commercial people are going to have to do this, maybe not until cellular telephone is 100 years old, though, or something like that, because there's a lot of time and energy in the cellular telephone networks as it exists. But I think it's a way that it's a good research topic for ham radio, and it's a way we can do a distributed network. Might be a way to do communications in like Antarctica or something like that, or I don't know, in places where there isn't already cellular phone on a professional basis. But it's something to look at. Antenna technology is always moving on. Spread spectrum processing gains, what chips you can do economically is always moving on. And the 1 megabit 14 dB GP 30 beam direction idea is, level is just what probably could be done today with $1 million worth of development. But it's just wanted to get all these ideas out before the world and see what grows from it. Thank you.
This seems to be...
Hold on, Carl. We got another question here.
At first blush, this sounds workable in an area where we have stations that are density is such that you have several nearest neighbors.
Right. Like most people who've gotten on packet usually have gotten on packet with friends, but yeah. And maybe not. What part of Minnesota are you from there?
Southeastern Minnesota.
So like La Crosse, Wisconsin area, or?
Yeah, just close to there.
Yeah. Okay.
Okay, and so we're facing a topography that's not flat.
So,
Okay.
Right. I know. Well, that makes it easier actually, because that means when you have those 3 stations lined up, that 4 stations lined up, that 4 station is going to be over the hill, because then you shoot to the guy there and he goes to the hilltop and then he shoots over the hill. So that actually makes it easier. I mean, you can share more readily than in Illinois because it's all flat.
Stations have to be on top of the hill.
Right. Well, even if they're in the valley, they shoot up to the top of the hill.
So they're all in the valley.
Okay.
People
Well,
live on the
then your interference limited, and you need to go to something like this. So eventually, or you can put up a regenerator on a hilltop, but then you got what's called the exposed terminal situation. Have you ever heard that term?
No.
Exposed terminal is when you got a simplex 14501 or something station that's on top of a hill, and you got all your users down in a valley. They try to use that repeater, but the stations on the other side of the hill or high enough, out in far distances, are transmitting to the station on the hill. The station on the hill is everybody, but nobody in the valley or out on the plain can hear each other, and so you always get a collision. And so that's been coined in the early days of packet radio. It's been coined as the exposed terminal problem, when a bunch of hidden. It just is a situation where Hidden stations are just where the stations can't hear each other, and because they can't hear each other, they're pounding this one poor station up on the tower, and they get very mad at you, especially if you're a BBS operator and you're trying to forward packets to St. Louis, and they're in Decatur and you're in Naperville, Illinois. So, but anyway, because they can't use their digipeater.
Well, we're using a bit region and a duplexer in order to minimize that.
Okay, yeah, repeaters. The problem in Illinois has always been repeater allocation availability.
With the problem here too.
Yeah, so I mean, we never. Every time we try to, there's only one. There's two packet repeaters, one on 440. One's used for transport. There's another one on 2 meters, but we tried to put up another one on 2 meters, and then we had our political problems because we were trying to do it in the packet spectrum, and a politically oriented packet competitor type like person threatened to call the FCC, so we had to pull it off. So I mean, it was self-defeating.
Well, actually, as I look at the band plan on the 2 meters, probably a packet repeater is probably not any place in the band plan.
No, you can use regular repeater allocations for packet. At least in Illinois you can. The problem is they've never given us a channel because the channel's already loaded. But there's been talk about these 10 gigahertz simplex repeaters in the Santa Barbara Microwave Society. They have these. But if you go higher and higher frequency, the attenuation between co-located antennas can be very high. In fact, enough that you can get a repeatable gain out of it. And they have this technique. They have one of these up where they have two beam antennas and like an 80 dB gas-fed amplifier between them, and the system is stable enough that it doesn't oscillate because the antennas are in a clear enough area that the near paths are not reflecting signals from one antenna back into the other. It just goes out into the valley. If you have nice hilly terrain like that, you can do like a 10 gigahertz ATV repeater that way. It'd be really nice for FM TV. OCARs, on-channel active repeaters. Okay. So that's a neat thing. That one might be a thing because then you could do 10 megabyte for a small environment, for a small locality. You could do a megabit at 10 gigahertz, and you're not efficiently using the spectrum, but you don't have requirements to either because you don't have zillions of people. Well, that would be a nice situation for you, because the other guys over behind the hill aren't going to get into it, because these antennas that have good front to side ratio typically have very good front to back ratio too. So, and Glenn Engen on his website, on his web information on the TAPR website, has all sorts of information about OCARs, about what they've done with them. And that's something that I think it's ideal for TV, because the TV is not time sensitive. I mean, the little bit of microseconds it takes to get up there and come back is not going to slow down the capacity of real-time TV. Where with a packet network over an area, it might. It's not that. It's because you got so many people and they all have so much traffic in a metropolitan area that you want to avoid using. The access becomes difficult because of the large propagation times, 40 kilometers, 20 kilometers up to the thing and back. So, but I think Glenn has solved the TV problem myself. And anybody who wants to do TV, I say, hey, why don't we do TV? I said, okay, let's go do an OCAR. And one of these days, somebody's going to say, hey, yeah, let's do it, and we're going to do it. But I still like DDMA for data. But you still, there's also ways where you can do translation on microwave frequency with phase shifters. So instead of having on channel active repeater, you could phase shift the whole spectrum of megahertz by a rapid phase shifter, and then come in at 1 megahertz and go out on another, and then you could get much more gain. So that's another idea for the future. But they apparently looked at that, but they couldn't get a practical phase shifter to do much frequency shift. So I guess that's it.